Yes, is my screen visible to everybody?
Yes, sir.
All right, so we will start now. So we will continue with the Rayleigh Ritz method. Okay. Till now, we have covered Rayleigh Ritz method for the bar problems, wherein we have seen the different cases like concentrated load, how to take care of concentrated load in Rayleigh Ritz method. We have also seen the surface load, and we have also seen the volume load. Okay, that is kind of a self weight. Okay, so now today we are going to see how to handle the beam problems. Okay, so now the basic difference between beam and bar problem is like bar is having only whenever it is loaded, it will be subjected to either tension or compression. But when it comes to the beam problem, it will be subjected to bending. Okay, so now for example, if you draw this straight line, okay, so this straight line can be a beam and this straight line can be a bar also. Okay, so now in both the cases, what we generally assume that this is your origin. Okay, this will be also your origin. Okay, but in case of beam problems, we generally assume this side as your x-axis. But in case of beam problems, we are not interested in what is going on across the length. We are interested in what is going on perpendicular to the length. Okay, so accordingly we have to assume the directions. Okay, so here we will be having, this will be your y direction. Okay, so basically we are interested in what is happening in the y direction, because the load will be acting in the y direction only, right? Now here what we generally assume is the displacement. So here what we generally assume, we assume this as u. If this is u0, then we'll call this as u0, and its direction will be either in the direction of x-axis or opposite to the direction of the x-axis, depending on the loading. But initially you just need to assume that the displacement u will be always parallel to your x-axis. It will be never perpendicular to the x-axis. But in this particular case, okay, in case of beams, we have, this is your x-axis, but in this case what is going to happen, that the deformation will be always perpendicular to the x-axis, isn't it? So either it can be in this direction or it can be even in this direction. Okay, so this is the meaning of this. So just to avoid the confusion, what we generally do, we call this deformation which is perpendicular to the x-axis, we generally denote it by a symbol called as w. Okay, and whenever the deformation is there parallel to the x-axis, we generally go for a symbol called as u. Okay, so now here this is the main difference between the beams and the bars. Now coming to the potential energy equation. So in case of beams and bars, both way, your total potential energy pi will be the summation of strain energy plus the work done. Okay, so now here the strain energy equation has to be defined. Okay, so let me write down over here. So this is strain energy. Okay, so this strain energy now can be written as u equals to, so if you remember, the generalized expression for the strain energy is half integration over the volume. We have sigma transpose into strain into dV. So this is a generalized expression for the strain energy. Okay, so now whenever you are dealing with the bar, so your sigma is nothing but your sigma x, and your strain is nothing but the strain, this will be strain symbol epsilon x. Okay, but when you are dealing with the beams, so in that particular case, this sigma will be now replaced by moment. Okay, and your strain. Okay, so strain will be replaced by a rotation. Okay, so generally this strain will be defined as negative d square w by dx square. Okay, so this is the expression which we have to write down over here. Now what is m? Okay, m is nothing but the moment, expression for the moment. So if you remember your second year strength of material, this m can be calculated as minus ei d square w by dx square. Okay, I hope you remember this particular expression. So now if you substitute all these values over here, so your strain energy U, okay, so your strain energy now can be written in this form, that is half, okay, this will be integration over the volume, okay. So let me write down the expression for the stress first. So expression for the stress is E, then I, we have d square W by dx square, okay. Then this will be multiplied by your strain, okay. So your strain is this one, okay. So this is again minus d square W by dx square, okay, and this will be into dV, right? Now since this is a 1D problem, so your volume, okay, so your volume can be written as area into length, okay. So if you consider this area as constant, okay, so if it is constant, so I will take this as 1. So your V will now become something like V is nothing but 1 into L, and if you go for the derivative of this, so this will be dV and this will be dx, okay. So dV will be replaced by dx now, okay. So with this you can rewrite the expression for the strain energy as this is half. Now this will be integrated over the length, okay, and this will be EI will of course come out. So let me write down EI outside because EI is constant. So this will be EI divided by 2. This will be d square W by dx square, okay, and this will be whole square now, and this will be now dx. So this particular expression will be used for the calculation of strain energy whenever you are dealing with the beam problems, okay. Now coming to the work done, okay, so this is work done, okay. So work done also has got some expressions which are very much similar to the expressions which we have seen earlier. So this has got work done, that is work done due to the point load, okay, plus the work done due to the surface load, plus the work done due to the volume load, okay, and everything has to be taken in the negative direction because otherwise your system will not be in equilibrium, okay. So now if you remember, we have written the expression for work done in case of bar whenever it is subjected to point load. We have written something like UI, okay, let me write down over here. So this is UI into PI, isn't it, where I can be any number of points, so I can be 1 up to n, okay. But this U is the deformation in the x direction, but since we are dealing with the beams, so this U now will be replaced by W, okay. So that is the deformation at a point, and this deformation will be the transverse deformation, that is perpendicular to the x-axis, okay. So this is how the expression is changing in case of beam, okay. Now similarly, of course, this will be negative over here. I'll put negative sign also over here. If you remember, for surface load, this is integration over the surface. This was U transpose into Fs over ds, okay. So here this U term is there, where U is basically displacement parallel to the x-axis. So we are not interested in that. We are interested in the what is the displacement perpendicular to the x-axis. So here this will be replaced with W, okay, minus the volume load will be exactly same as previous one. Only thing is, in place of W, in place of U, you have now W transpose. This will be FV over dV. So these are the some changes which we have to make when you are solving the beam problems, okay. And of course, your strain energy plus work done will give you the total potential energy, and this total potential energy should be minimum in order to maintain the equilibrium, and that can be achieved by going for the derivative of this total potential energy with respect to the constants, which will eventually come when we will be solving the problems part, okay. I hope this is clear to everybody. Is there any questions, or shall I continue? Yes, students, is there any questions? Okay, I guess not. So let me continue and let us take a simple problem. So I want all of you to do the calculations along with me, okay, so that you can understand the things in a better way. Okay, so let me start a problem now. Okay, so this is my problem. Okay, so now I am going to take a very simple problem. So I'm going to take a cantilever beam. So let us say this is my cantilever beam over here. Okay, so we have a fixed support like this. Okay, and then we have a load of, let us say, 100 kilonewton, which is acting at the tip of the beam. Okay, then let us consider the dimensions. Okay, so let us consider this dimension. So for example, this dimension is 5 meters. Okay, so this is 5 meters over here. Okay, and let us consider the axis. So this is my axis, which is like this. Okay, let me slightly move this up. Okay, so this is my axis, and let us call this is your x-axis. Okay, so in this direction we are going to assume your x-axis will be having origin over here. Okay, so this will be the origin of the axis, and we have to analyze this using Rayleigh Ritz method. And in this particular case, the value of E and I both are given. Okay, so your value of E is given to you, that is modulus of elasticity, that is 2 into 10 to the power 5 kilonewtons per meter square. Okay, and the value of I is also given to you, that is 10 into 10 to the power 8. This is millimeter to the power 4. Okay, so this is what is given to you. Okay, so now we will just try to solve the problem using the Rayleigh Ritz method over here. Now in the very first expression in the Rayleigh Ritz method is, we have to assume the polynomial for the displacement. Okay, so let us start with the solution part now. So this is, okay, so this is my solution. So if you remember, initially we used to assume the value of u. Okay, so generally what we used to do, like u is equal to a0 plus a1x plus a2x square plus a3x to the power 3, and so on. Okay, so this is what we used to assume. So depending on the type of the problem, we have to assume this. Okay, but now since we are dealing with beam, so this u will be now replaced by w. Okay, because w is the deformation in the transverse direction, right? So this is the main thing, main change over here. So now let me draw a free body diagram for the given problem. Okay, so for this purpose, I'll just take a simple bar, which is like this. Okay, now let me write down the coordinates first. So let us call this is your first node and this is your second node. Okay, because I'm not considering any node over here, so let us call, I think we can go with 0 in place of 1. So let us call this as node number 0, and this is node number 1. So it doesn't matter, you can give the numbers 1 2 also, that is not an issue. Okay, so if you call this as node number 0 and node number 1, so here this is your fixed joint. Okay, so this x will be called as x0 and its numerical value will be 0, and this x will be called as x1 and its numerical value will be 5 meters. Okay, because we are considering axis at this particular point. Okay, so this is the deformation, this is the your values of coordinates as far as w is concerned. Okay, so here w will be called as w0. So w0 is what? It is nothing but the transverse deformation at that particular point. So I am talking about the deformation in this direction. Okay, so since this is fixed end, so the value of w0 will be 0. Okay, and coming to this part, so w here at the point number 1, it will be called as w1, and its value is still unknown, because at that point there is no support over here, and at the same time there is a load which is acting at that point. So because of that, there will be a possible deformation, and the value of that deformation will be known only after you get the solution of the given problem. Okay, so this is the free body diagram. Now the first thing what we have to do is, before solving the problem, we have to apply the boundary conditions. Okay, So coming to the boundary conditions, we have 2 points. Okay, one is point number 0 and second one is a point number 1. So here let me write down like at point number 1. Okay, so at point number 1, what we have, the value of x is 0 and value of w is also 0 over here. Okay, now so if you substitute this in the expression which is written over here, so this is the expression for the deformation, isn't it? So at this point, so w is 0, so I'm going to write down 0 over here. This will be a0 plus a1 into x will be 0 plus a2 into x, or x value will be 0. Okay, we have not yet assumed this one, the expression we have not assumed, so let us assume the expression up to 3 points only. Okay, so let us assume that our expression is this expression. Okay, you can assume as per your convenience, you can assume only a0 a1, or you can assume a0 a1 a2. We can assume this one also. So I am going for the slightly higher order equation. I am going for up to a3. Okay, so this expression will be now a3 into 0 to the power cube. So if you solve this, what you are going to get is a0 equals to 0. Okay, so the final expression of w, that is the deformation in the transfer direction, now it will take a shape of a1 into x plus a2 into x square plus a3 into x to the power 3. Okay, so let us call this as expression number 1. Okay, so this is expression number 1. Now, is there any other boundary condition which is available over here? Anybody? Any guesses? Okay, I'll tell you. So here one more boundary condition is given over here, that is the rotation. Okay, or rotation, or I can say slope. Okay, so whenever you have a beam, it will be subjected to a bending, and because of the bending, the shape of the beam is going to change. And if you go for dw by dx, so it is going to give you a slope, isn't it? So if you go for slope, or you can call it as a theta, so at this particular point, okay, you have a theta value. Okay, so here we have a theta value, here also we have a theta value. Okay, now you see, if you consider the fixed joint, so this will be called as theta 0 and it will be 0 because this is the fixed joint. So irrespective of the loading, there won't be any rotation at this point. Okay, and as far as this part is concerned, you can have theta 1 and its value will be unknown. So this is one more boundary condition which is available with me. So we can go for this boundary conditions also. So we can apply at that particular point. We also know that the value of theta is 0. So theta is also 0. So we can write one more term over here, theta as 0. Okay, so for calculation of theta, what we have to do is we have to go for dw by dx. Okay, so since this is my w, so I can go with dw by dx over here. Okay, so if this is dw by dx, so let me go for the derivative of this. So this will be a1, okay, plus, so this will be 2 times a2 into x, plus this will be 3 times a3 into x square. Okay, so this is the first derivative of the w with respect to x. So now we can apply the boundary condition over here, that is at point 1. What is there? The x value is 0. At the same time, the theta value is also 0 over here. So this value, that is dw by dx, is nothing but your theta. So this value is 0. So we can have a1 plus 2 times a2. The x value is 0 over here, plus I think this is 3 times a3, and x square value, this will be also 0. So if you solve this, so what you are going to get is nothing but this as 0, a1 value as 0. So initially we have calculated the value of w as a1x plus a2x square plus a3x cube. So now finally the value of w can be written as 2 times a2 into x. Okay, oh sorry, not 2 times, only a2 into x. This 2 will not come into picture. Okay, and plus a3 into x to the power 3. So this is nothing but your expression number 2. Okay, I hope this is clear to everybody. Is there any questions as far as this part is concerned?
Sir, a2x square.
Sorry, a2x square, my mistake. That is a2 into x square. Okay, so this is the final expression for the value of w, right? So we have applied both the boundary condition. There is no other boundary condition available for this problem. So now we can go for the calculation of the strain energy. Okay, so let me write down strain energy. Okay, so this strain energy is usually denoted by a symbol that is U. And if you remember, for beam problems, just now we have gone for a derivation. So this comes out to be EI divided by 2 integration over the length, and this will be d square W by dx square. This will be whole square into dx. So this is the expression for the strain energy. Okay, so now first of all we need to find out what is d square W by dx square. So we already know what is the value of W over here, isn't it? So we can go with dW by dx over here. So this is 2 times a2 into x, plus this is 3 times a3 into x to the power 3. I hope this is correct. Then again, if you go for a derivative of this, so this will be d square W by dx square. So this is going to give you something like 2 times a2 plus this will be, I think I have made a mistake over here. This should be x square, not x cube. Okay, so this will be 6 times a3 into x. Am I right? Barabar hai ye? Okay.
Yes.
Right.
Yes, sir.
Fine. So now we will go for the strain energy expression over here. Okay, so this strain energy now can be written as U equals to, we need to have the EI by 2 value also. Okay, so this is EI by 2 integration over the length. So this will be from 0 to 5, because our length of the cantilever beam is 0 to 5, and this is d square W by dx square value. So this is nothing but 2 times a2 plus 6 times a3 into x. This is whole square over dx. Okay, so this is the meaning of this, right? Now let me calculate EI by 2. So if you remember, these values are given to you. So this is EI divided by 2, right? So the value of E is given in kilonewtons and meters. So let us keep all the units in, let us say force unit we will keep in kilonewtons, and the distance unit you will keep it in meters. So this is okay, but this is not okay. Okay, so we can rewrite this particular expression. So this is 10 into 10 to the power 8 millimeter to the power 4. So this can be converted into meters, that is 1 into 10 to the power minus 3 meter to the power 4. Okay, so if you want, you can now calculate over here. This is EI divided by 2. So E is something like 2 into 10 to the power 5. Okay, so this is 2 into 10 to the power 5 multiplied by 1 into 10 to the power minus 3 whole divided by 2. This will be cancelled, and at the end what you are going to get, something like 100. Okay, is it fine? Is it okay?
Yes, sir.
Okay, so this PI upon 2 is nothing but here 100. Okay, now so let me go back over here. So your U value, so this will be 100. Okay, this will be from 0 to 5. This will be 2 into 2 is 4 times a2 square, plus this is 6 into 2, that is 12 times. This is a2 a3 into x, plus this is 36 into x square, and this will be dx. Is it okay? Fine. So now we just have to go for the integration part, right? So let me do the integration part now. Let me slightly go down over here. So if you go for, yes,
Sir, 24.
Sorry,
24.
सर 24 होगा
सर की जगह 24.
और सर 36 A3 स्क्वायर भी होगा.
36.
A3 square.
Sorry, I'm not able to get it.
सर 12 की जगह 24 होगा और 36
Oh, right.
36 एक क्यूब 36 एक A3 स्क्वायर भी होगा.
Okay. So this will be 24, right? Okay, and this will be A3, and this will be x square. Okay, this will be also square, and this will be also square. Correct? Okay. Fine.
Yes sir.
Thank you. Okay. So let me go for a integration now. So this will be 4 times A2 square, and this will be only x. So this will be from 0 to 5, plus this will be 24. This will be A2 and A3. So this will be x square divided by 2. This will be also from 0 to 5, plus we have 36 A3 square. Okay, and this will be x to the power 3 divided by 3. This is from 0 to 5. Okay, so can somebody tell me the final answers, please? I don't have the answers today, so you have to help me out. Okay. Yes, somebody please tell me. This will be 100, which I am taking outside. So this is 0 to 5. So 5 into 4, that is I think 20. Okay, so 20 times A2 square, plus this is 12. So this will be कितना आ रहा है? 300.
300.
A2 and A3. Okay, fine. Plus ये कितना आ रहा है?
1500.
1500. This will be
A3 square.
3 square. Okay. So this will be the final expression for the value of u. Okay, I hope this is clear to everybody. Is there any question? Let us call this as expression number A. Right, now coming to the work done part. So let me slightly go down over here. So this is now work done. Okay, so generally this work done has got 3 components. Okay, so work done is generally denoted by a capital W. So this will be something like minus, this will be the point load, then we have surface load, and minus we have the volume load. Okay, so as far as this part is concerned, there is no surface load, there is no volume load. So what we have, only the point load, and this point load is denoted by a symbol Wi and Pi, where this I is nothing but the point of application where the load is there. Okay, so if you refer this particular problem, so in this problem the load is acting at a distance of at point number 1. Okay, so this is point number 1. So this expression will now become something like minus W1. Okay, not I, W1, and then P1. Right. So now the first thing we need to calculate it is what is the W1 value. Okay, that is what is the displacement at the point number 1. We already have the value of W, isn't it? So we have already calculated the value of W. This is the latest value of W, that is expression 2. This is A2x square plus A3x cube. Okay, so this is let me write down over here. This is A2x square plus A3x to the power 3. Okay, so when if we want to calculate the value of W, so in that case we have to reach to the point where the point is there. So at point 1, okay, so at point 1 the W value will be called as W1, its value will be unknown, and your X value will be called as X1, and its value is known to me, and its value is nothing but 5. Okay, so if you substitute these values over here, so W1 will be something like A2 into this will be 5 square. Okay, plus this will be A3 into 5 to the power 3. Okay, so your W1 now can be easily written as something like this is 25 times A2 plus this will be 25 into 5 is 125 times A3. Okay, so this is the expression for the value of displacement at point number 1. Okay, so if this is known to us, then what we can do is this one. Okay, that is the work done. Okay, so this capital W now can be written as minus, this is W1. Okay, so W1 can be written as something like 25A2 plus 125 times A3. Okay, now what is the value of P over here? That is, P is nothing but the point of application of the load. Okay, so here the load value is 100 kilonewton. Okay, so this is your 100 kilonewton. So let me write down 100 over here. Now it is acting vertically downwards. Okay, so this is acting vertically downwards. So what we can do, first of all, we need to assume that whether this W is vertical or whether W is downwards. Okay, so here I have given you vertical. Okay, here I have given you vertical, but if you want, you can assume this as downward also. So let us assume this value of W is acting in the downward direction. Okay, also your y-axis or your w-axis is nothing but over here. So if this is your w-axis, in that case you see the value, the direction of this load and the direction of this w-axis, it is same. So since it is same, so we have to take the value of this w as positive value. Okay, if it is acting vertically upward, so in that case you have to consider this as negative. Okay, so if you rewrite this expression, so value of w will now become let us say something like minus, so this will be 2500 times A2 plus this is 12500 times A3. So this is the expression for the work done. Okay, I hope this is clear to everybody. Now coming to the total potential energy.
Sir, minus 125.
Oh yeah, it should be minus, correct. So this is total potential energy will be the sum of strain energy, okay, plus work done. Okay. So he has rightly pointed out the value of this value should be negative. Okay, fine. So here this pi value, okay, so this is pi value now can be written as something like this. Okay, so I will have to write it down over here. So this will be 100 into, this is 20 times A2 square plus 300, this is A2 A3 plus 1500 A3 square, so this is the strain energy, minus work done will be 2500 A2 minus 12500 A3. Okay, so this will be the expression for the values for the given problem. Okay, now so if you want to know what are the unknown constants, that is A1 and A2, so in that particular case we should have the total potential energy as minimum, and you can get the total potential energy as minimum by going for the partial derivative of total potential energy with A1, also with A2 and A3, and equating it with 0. Okay, so we have d pi by d A3 will be 0. Okay, so can you so this is going to give you one equation, this is also going to give you one equation with this A2 and A3, this will be also A2 and A3. You just have to solve this and tell me the value of A2 and tell me the value of A3. Okay, please do this. I don't have the value, so please do the calculations and let me know the values. Yes, anybody has the answers?
So 1.25 and minus 0.0833.
Let me write down, huh?
1.25
This is 1.25 and this is
minus 0.0833.
minus 0.0.
833.
Okay, somebody please cross check these values.
Correct है sir.
Yes,
Correct, huh?
sir.
That's very nice. That's very nice. Okay, so we will continue now. So if you remember, we have already calculated the value of W in terms of A1 and A2 over here. Oh, sorry, this is not the W. Okay, that's a different W. Okay, W is nothing but your expression 2. Okay, that is A2 into x square plus A3 into x to the power 3. Okay, so let me slightly go down. So now since we have the values, let me substitute the values. Okay, so your W is something like A2 into x square. Okay, so A2 value is 1.25 x square plus your A3. Okay, so your A3 is nothing but minus. Okay, so this will be minus, this will be 0.0833 into x to the power 3. So this is the expression for the deformation. Okay, so now let us substitute these values and we will see how the deformation is. Okay, so let me draw a straight line over here. Okay, and so this is nothing but x equals to 0 and this is nothing but x equals to 5 meters. Okay, so at this point if you substitute the value of x equals to 0 in this expression, so I'm talking about this point. So here if you substitute the x value as 0, here also x value as 0, so you'll find the deformation is 0 itself. Okay, so since there is a fixed end, so there is no point or because of that fixed support there will be a zero deformation in this at that in this point. Okay, so let us now substitute x equals to 5. Okay, so if you substitute here x equals to 5 and here also x equals to 5, so can somebody tell me how much is the deformation values, please?
20.8375.
Okay, so this is over here, so this is negative or positive?
Positive.
Okay, so positive means remember we have assumed the w direction like this. Okay, so here this will be something like 20 point kitna hai?
8375.
8375. Okay, so this is the deformation at the free end. Okay, so this is a third degree polynomial because x cube term is there, so all we have to do is we just have to join this like this. Okay, so ideally whenever you see a cantilever beam it should deflect in this pattern only, and if you solve the problem using any of the software you should get these value, that is 20 point something, because I remember I have solved this problem in STAD and then I got this value. Okay, the same value I have obtained over here. Okay, I think there is some mistake with the units conversion, because ideally this should be the value should be in meters. Okay, so this much meter deformation should not come. I think there is some issue with the power term. Okay, so I think we missed 10 to the power 3 somewhere. Because of that this difference is there.
Sir, due to the value of E.
Due to the value of
E. Because
E.
it is given in kilonewton per meter square. That 2 into 10 raised to power 5. It should be in Newton per mm square.
Okay, quite possible. Okay, anyway, so all I'm trying to say is that there is some issue with the power term, otherwise the value, numerical value is perfect. Okay, so this is how you can get the expression for the deformation. Okay, I hope this is clear to you, everybody. Is there any questions as far as this part is concerned? Okay. Okay, so today we have just learned how to solve the beam problem. Tomorrow's class we will continue with the beam problem. Tomorrow we'll take a simply supported beam, and not tomorrow, in the coming class, and we will see two different approaches to solve the problem of simply supported beam. Okay, so I think that's it for today, and if you have any questions you can remain in the Google Classroom, Otherwise, you can